Welcome everyone to the TEP's first event this school year. So first, I am with the Center for Excellence in Education, which was founded in 1983 by Joanne DeGennaro, who is still our president, Admiral Rickover, who's the father of the nuclear Navy. Our mission is to nurture high school and university scholars to careers of excellence and leadership in STEM. And we offer three costly programs in the United States: the Research Science Institute, USA Bio-Olympiad, and the Teacher Enrichment Program. Science Institute, or RSI is what we usually call it, is a highly competitive 6-week summer science and engineering program that is open to rising high school seniors. So they apply in their junior year. And we host it at MIT, and students actually just complete a 6-week research project with mentored professors and researchers and scientists. This past 2 years, we've done it virtually because it went really, really well, and some kids did some very, very interesting projects. Participants of the program go on to do really well at like the Regeneron and Siemens type competitions, with many going on to advanced STEM degrees, although being a lawyer is also very popular. Registration opens in mid-November, and applications are usually due early January. Next, we have the USABO, and the USABO is the nation's largest biology education and testing program. We encourage everyone to explore the world of biology through the USABO. It's a series of examinations testing students' knowledge of biology concepts. And lastly, today we have Carrie Prashant, who is the Director of STEM and Outreach at James Madison University. We also have Bill Lukens, Professor of Geology and Environmental Sciences at James Madison University, and Dan Tyler, who is a program manager at the Department of Energy's Office of Science. So we're thrilled to have all three of them.
So I am Bill Lukens, and I'm an assistant professor in the Department of Geology and Environmental Science at James Madison University. My pronouns are he, his, and what I do in my research world is I look into the geologic past and reconstruct what the environments and the climates used to be here on Earth. I thought today for the virtual bite of science, a glimpse into how we teach about Earth systems and climate change. We have a few different courses related to this topic, and I thought that a lot of people don't actually have access to the most up-to-date information on anthropogenic climate change, what's going on today, and how it impacts our lives, and what role we play. And so I thought I'd give the most up-to-date science. And for myself as a public servant here, I'm employed by the state of Virginia. So if anyone's interested, you can reach out anytime for information, chats, whatever you'd like. Okay, so in this presentation, I'm going to ask and answer 4 questions. How do we know climate is changing right now? Are we humans to blame for this change? And how did COVID lockdowns affect emissions and subsequently climate change? And what can we do about all of this? Things have, and I can say from my perspective, I've been teaching about climate change for over a decade now. The landscape of climate change education is very different depending on where you are. I've taught in Texas, Pennsylvania, and Virginia, in a variety of different types of higher ed institutions. And what I will say is right now, students are very, very in tune with the changing climate and their role in it. And that has been a rapid change over the last few years. So the first question, how do we know that climate is changing? And there are 3 ways we can get at this answer. The first is called the instrument record. And these are just direct measurements from the instruments that we have deployed all over the Earth, and also the satellites that we have hovering above the Earth. And so what we have shown here is on the temperature record, and this is displayed as temperature change relative to the temperature change from 1960 to 2019. And it's a global record. Warmer colors mean the temperature is increasing in that area, and cooler colors means the temperature is decreasing in that area. And I'd like you to take away 2 major points. The first, all over the world, the colors tend to be warmer. And so we are measuring over the last several decades an increase in temperature all over the world, with the exception of very, very few places. One is what we would refer to as the global warming hole over central Antarctica. And that's a real feature. and it's on the subject of a lot of intense study. But the rest of the world is warming quite rapidly. And the second thing I'd like you to take away from this is that the patterns are not homogeneous. This map is not all one shade of yellow. It's not one shade of orange. The continents are warming faster than the oceans. All the continents are more orange. The oceans are yellow. And up near the North Pole is bright red. The Arctic area is warming at roughly twice the rate of the rest of the world, as per our measurements. Okay, but this only goes back to 1960, and one may ask, well, the Earth is 4.6 billion years old. Can we get a little perspective on this? Does this matter? We can step back in time a little further back before instruments, but while people are still around making observations, because we trust our friendly fellow humans. And so what we have on the left here is a graph. On the y-axis is the temperature, and it's just temperature change over the last 2,000 years. And these are in degrees Fahrenheit. 0 would be no temperature change. So if the temperature hadn't changed on Earth since the year 1 Common Era to the year 2020, this would be a flat line at 0. Anything below 0 is cooling relative to the long-term record here. And anything above 0 is a warmer interval. There's a couple really interesting patterns here. So since the year 0, essentially, climate was pretty stable with some wiggle. And, that was wiggle on the decadal to century scale. And then there's this interesting dip. This dip is what we refer to as the Little Ice Age. And it occurred between the 15th to 18th centuries. So that's roughly the 1400s to the 1700s. Interestingly enough, this shows up in portrayals of the time. So here's Washington's crossing of the Delaware. Granted, this was painted in the mid-1800s, but I'm from southeastern Pennsylvania. I've been on the Delaware River. It is very hard to find chunks of ice floating in the winter on the Delaware River. But we take this to be at least a roughly accurate portrayal. This is not the only example. The Dutch Gilded Age painters, when landscape painting became a thing, it was actually all these beautiful, iconic winter landscapes that were painted, and that was during the Little Ice Age. However, since the 18th century, what we have observed is in historical records, and then in the instrument record, a very, very rapid rise in temperature. This black line here, this little tiny black line, that is the instrument record. Everything before that is reconstructed from what we call paleoclimate proxies, which are things that we can measure from the past that are affected by climate, but are not actual thermometers themselves. So they have some uncertainty, and that's what this hatched window is. Right now, the warming we are experienced is unprecedented in the last 2,000 years of our records, without question. We can dive even farther back in time into what we call the deep time paleoclimate record. Deep time is far before humans even evolved. It's before the last 2 million years. And so it's going back into very strange times in Earth's history, very deep in time. So this is the geologic record. This graph is showing on the x-axis, 0 over here, this right side is us right now. And we're stepping back in millions of years now, back to 100 million years ago. This is still a tiny fraction of Earth history, but it's a large fraction of life as we know it in recent times. For reference, the dinosaurs went extinct at 66 million years ago, so about 2/3 of the way to the left. The gray line is atmospheric CO2, and this is estimated from paleoclimate proxies from a large variety of methods that complement one another. And here we are on the right axis. CO2 level is portrayed on the right side. The line above the CO2 curve is the temperature curve, and that axis is on the left side. The first take-home point of this graph from the geologic record that I want you to see is that CO2 level and temperature are intimately linked. Not every little wiggle matches exactly because our methods of reconstructing these vary, our resolution varies, but overall, higher CO2 means higher temperature. And then the second really big take-home message, and this is one of the biggest misconceptions I dispel in my students all the time, is that right now, we're at CO2 levels of 415 parts per million, and the average Earth's temperature is about 15.5 degrees Celsius. That's right now. If we go back in time, we have to go back about 23 million years to get to CO2 levels that are as high as they are now. So yes, in the recent geologic record, CO2 levels are exorbitantly high. But before 23 million years ago, the normal condition is that CO2 levels are far, far greater than they are today, upwards of 500 to 1,000 parts per million. That is a very large fraction of the Earth's atmosphere. But what comes with that is that the temperature of the Earth is much, much, much higher than it is today or in recent times. And so if we want to call this the normal condition of Earth history, normally CO2 levels are higher, temperature is much higher than today, and there are no ice caps on the poles. We humans have a little bit of a biased record here from our own observations. When we step back in geologic time, what we do is we reconstruct what the environments used to look like, and we can make what are called analog comparisons. So an analog is just a representation from a different time or place. For example, 55 million years ago, there was a rapid warming event that we call the Paleocene-Eocene thermal maximum. Thermal maximum doesn't mean that it got as hot as it ever did in Earth's history, it just means it was this big spike in temperature. And in the Arctic, the environments had crocodiles, cypress swamps. It looked very akin to what we see in South Carolina today. And so South Carolina is a modern analog for what the ancient Arctic looked like in this ancient warm interval. And right now, because of our burning of fossil fuels, we are starkly on a pathway that may return us to a climate state similar to the Paleocene-Eocene thermal maximum. Okay, so the next logical question is, are we humans to blame, or is this a natural process that is occurring? Here's the record of atmospheric CO2 for the last 800,000 years. Again, we're at year 0 here. This is in years before present. This red line is the instrument record. This is what we've measured for CO2. And the blue line is little heartbeat. These are from bubbles from ice cores that have been dated. Couple take-home points here. There's this maximum level of about 300 parts per million that we've seen through all of the last variations for the last almost a million years. Every time CO2 goes up, that's between the ice ages. When it goes down, that's one of the ice ages. And you can see there are many, many ice ages that have occurred over the last several 100,000 years. At the peak of the last ice age, CO2 levels were 180 parts per million. That was about 20,000 years ago. Before the start of the industrial era, CO2 levels were 280 parts per million. So that's roughly the year 1750. This massive increase that we've seen, such that right now, roughly 45% of the CO2 in the atmosphere is a result of fossil fuel burning and other human activities, has only been a very, very recent feature in the Earth system. And we've documented this drastic rise at observatories all over the Earth. And so this is a very recent and very, very rapid change that's been occurring. So are we to blame? Well, we can go back to this temperature record reconstructed for the last 2,000 years that I showed you recently, and we can look at this rapid temperature rise that's occurred recently. Computer modeling has gotten so good recently that we can actually simulate natural systems and the anthropogenic systems very, very, very well, to the point where we can make a fake planet Earth that removes the burning of fossil fuels, the removal of large forests, the paving of landscapes, changes in essentially all human activity. And we can look at what just the natural forcings on the climate system would look like, and that's solar activity and volcanic eruptions. And over the last, since 1850, during this rapid rise in temperature, there would be no temperature change. But if we include human activity and everything we know about the amount of emissions that humans have caused, that is when we can actually get this uptick in temperature coming out of the model simulations. That's the brown line. This black line is the observed temperature that we've measured. And so we can't actually replicate Earth's temperature change without including human activity. And this is kind of like a silver bullet for saying people have to be part of this equation. Nothing we know about how the Earth system functions can give us the right answer if we don't include human activity. What's really interesting, and I want to bring this home to a lot of us here because my assumption is we're all in North America right now, or most people here are probably in North America. In the world today, the standard of living, this is represented as GDP per capita, is shown on the y-axis. The x-axis is essentially the energy consumed by people living in these countries. What we see is that essentially richer nations consume more power. If anyone's ever visited a developing nation, as I do practically every summer to do field work, I see that the individual people tend to use very little power. People are not driving around in large pickup trucks. They're not watching flat screen TVs as we are in North America here. And so North America per capita is using far, far more energy than any other place in the world. And it's easy for us to say, oh, well, areas that have rapid population increases right now, like sub-Saharan Africa, must be to blame for all of this energy that's being used right now. But blaming an area like sub-Saharan Africa, which is on the very small end here of the energy consumed, really ignores our historic role in modifying planet Earth's atmosphere. This is an interesting question that scientists are trying to access right now. How did the COVID lockdowns impact greenhouse gas emissions? This is another way of asking, okay, if humans shut off the valve on our activity in releasing CO2, can we get some insight into whether or not we're impacting the climate system? This is a plot of global fossil CO2 emissions on the y-axis. And this is from 1960 on up to the projected 2020. These data come from the Global Carbon Project from the end of last year. And we can see that there's this steady rise with some ups and some more rapid ups and some less rapid ups, but always ups. So every year on year, we're emitting more CO2 with very, very few exceptions. In the 1990s decade, we were emitting an increase of almost 1% per year. In the early 2000s, we were going gangbusters at 3 times that rate, and then we cooled off a little bit more recently to around a 1% increase per year. And then COVID happens, and we have lockdowns all over the world. And there was a projected, and the numbers are spelling out to be pretty similar to this, there was a roughly 7% decrease. This is an unprecedented decrease since we've been keeping these records. This is by far the largest reduction in CO2 emissions since we have records. However, will it impact Earth's atmosphere writ large in these long-term trends? From 1960 until right now in 2021, we have the records of the actual CO2 in the atmosphere. These heartbeats that you see are seasonal variations. I could go into more detail about that, but it's just essentially plants growing and senescing throughout the year. This is a steady rise, and we see that the steady rise is clearly continuing on through 2021, and the decrease we see here in the summer is on the order of regular decreases. So I do not think that the COVID lockdowns are actually going to have a long-term impact on this drastic CO2 rise that is occurring. And you can ask yourself, did I continue to drive to work even though there's a pandemic happening? Do I drive to the grocery store? Is the electricity on? The answer is yes. This is a plot of annual CO2 emissions from 2018. And so these are in billions of tons. And this is going back from the start of the Industrial Revolution until 2017, 2018. Right now, a lot of people are putting blame on China because currently, right now, they are the largest emitter of greenhouse gases. And that's because they've had a very recent rise. And it was only just a few years ago that they surpassed the United States in the amount of CO2 emissions. I'd like to dispel this myth that we should all be pointing fingers solely at China right now, because we can look at this in a few different ways. If we look at per capita CO2 emissions, okay, allocate each person a certain amount of greenhouse gases and associated warming. The United States remains far, far above China, which is this blue line here. And China only recently passed the United Kingdom in this regard. And so each individual person in the United States has more blame on their shoulders, even today, than each individual person in China. And so this means that we should be taking this seriously as American citizens and participants in the world economy. Okay, so this question now becomes, what do we do about it? I don't like to be all poo-poo, ho-hum, the climate is changing and it's all our fault. The honest to goodness truth in how this works is every little bit of CO2 we release contributes to global warming. And it's because the sinks for CO2, the places that soak up CO2 in the Earth system, are rapidly filling up. And they are getting not quite as good these days at pulling down CO2 because we're doing things like cutting down forests, and those pools that can store carbon are rapidly getting full. These colored zones are different scenarios that we can walk down moving forward into the future. The x-axis is the cumulative amount of carbon going into the atmosphere since 1850, so since early in the Industrial Revolution. The y-axis is the amount of warming. Every bit that we add to the atmosphere contributes to warming. The only thing we can do is to cut it out, and we have to slow this down. The only way to slow down warming is to slow down the amount of CO2 emissions that we are releasing. If we walk down this path that a lot of us refer to as business as usual, whether or not the dark red or the light red is business as usual in your framing, depending on the scientist or the analysis, that varies. Either way, neither of those scenarios is very good. It's going to put us in a place where we're looking at really dramatic warming by the end of the century, and we will be firmly on a path of looking at something like the Paleocene-Eocene thermal maximum occurring within the next several centuries to 1,000 years. So that's entire melting of the Arctic, crocodiles having a happy place in northern Canada, versus making drastic changes now, which will limit a lot of those bad impacts. This is kind of like if you're trying to pay down debt on a credit card. You can't just say, I'm going to start paying down the debt on the credit card at some nebulous point in the future. The more you pay down now puts you in a better place in the future. We don't take out a 30-year mortgage on our house and start paying it in year 29. What's going to happen in the future? If we reduce emissions, so we're in Virginia right here, at least I am, maybe some of you are as well. If we reduce emissions, the late 21st century versus mid 21st century, we're still going to see warming occurring. It'll likely warm by a few degrees, a couple to a few degrees by the late 21st century in the best case scenario. If we keep increasing emissions, we may be looking at mean annual temperature increases by the end of the century of several degrees Fahrenheit. That will be a drastic change. A lot of that warming will occur at night and during the winter. Another thing that's really alarming is the patterns in rainfall increases. So the total amount of rainfall may or may not change in a lot of areas. It'll likely go up. However, what the science is saying, and a lot of the recent modeling is saying, that most of the rain that falls in the heaviest 1% will be a bigger portion of our total rain. And so it'll rain harder, more briefly, in a lot of the areas of the world, including Virginia, as the atmosphere of the Earth and the temperature change. That's alarming for our infrastructure. And so we have to think about that right now. So what can you do about it? Okay, no one on this call caused the Industrial Revolution. I did not wake up someday and design a coal-fired power plant, and neither did you. And so we need to dispel this myth that it's like all of us feeling guilt for where we are now. However, even today, in this moment, you and I on this call are consuming far more energy than the average human on the planet. And so we have to think about what we are doing right now. In order to combat climate change, this is going to be an all hands on deck. We really need the government, large governments, the richest governments in the world, to take fast action right now. I would love to buy an electric car. I cannot afford one, and I can't charge one easily when I travel. That is infrastructure that we need to think about. Other things that we can do. I'm in a one-car family. My wife and I, we have a small hatchback that's a used car. We drive it infrequently, and I bike to work as much as possible. We ride share. I came to work at 5 this morning because she took the car to Richmond. It's a decision we make. It's a lifestyle that I want to live. We try to eat less meat. We want to switch to an electric car when we can. we try to avoid flying on planes as much as possible. Saying to someone, have one fewer child, I think that's like a weird existential thing to be talking to people about, because birth rates are declining anyway in the rich countries. This pattern that we see during the pandemic of CO2 going up and up and up, and then the unprecedented decrease, is something that can be a story for us all. This decrease was largely driven by less people driving in cars. The largest share of CO2 emissions right now is from people driving in cars and our whole transport infrastructure. And so that is something that you can do. The other thing I'll say is just pick something that you're into, pick something you like, and stick with it. Being sustainable about your actions is more important than burning yourself out and blaming yourself too much. Thank you for your time. I'm Bill Lukens. Here's my email address is lukenswe@jmu.edu. If you Google search JMU paleoclimate, you can get a hold of me via my website. Reach out anytime. I'm happy to answer any questions on this call or otherwise. Thanks.
Fabulous. Thank you so much. So some questions. Also, if anyone out there also has questions, please submit them to the chat, and I will ask them. So when you had showed a graph about that was CO2 emissions per capita, and that was it, and I assume that's sort of like total U.S. or each country's emissions. How do those numbers change per capita if you kind of like, I guess, try to take out like that industrial like CO2 production?
Oh, so like how does one person's individual actions change? It's an interesting question. There are weird anomalies that pop up when you include like all industrial activities. Like the United Arab Emirates is one of the highest per capita emitters because they have few people and very fossil fuel rich economies. I'm not that much of a sociologist, so I don't know how to break all that out, but I would say that the light switches we turn on and the coal-fired power plants that we're utilizing are part of our individual energy budgets, and a Canadian is not using my power plant.
Okay. And then, oh, Vincent, just so you know, yes, I do ask for presentations and I post everyone's slides. So you should have you'll have access to Bill's slides. So you can share that with students. Teachers are very excited. I don't know if you see the chat about sharing a lot of this with students.
And I'll put some links in the chat too that are data sources where I got some of this information as well, but feel free to use the slides for sure.
Yeah, and then I will absolutely, so I'll definitely, like, I'll post the recording, I'll post the slides, I'll post any links that are shared here, and everyone gets, I will also email you guys Bill's contact information so you don't have to seriously write things down that were from his slides. Okay, so someone has a question. What about, like, you know, people like houseplants? Like, I guess, like, if we all got like a whole bunch of houseplants, like, what impact might we see?
I would say that the houseplants will definitely make us feel better as we contend with these very large scale issues. My house is littered with houseplants. I garden all the time. My gardening is not trapping CO2 on some level to make a difference, but it makes me feel good and balances me so I can come and educate people on climate change and interact with students and lead a happy life. And that is a very important thing.
Awesome. So a question here about, I guess, like, what, like, your thoughts on some of our, like, kind of like our ideas around like carbon capture.
It will utterly be necessary. At this point, we've essentially, and I alluded to this a little bit in the timing of the CO2 increase, but didn't explicitly say it. We're performing a really like mad scientist experiment right now, where we've let off the valves on the gas tank and put all this CO2 in the atmosphere. And it is, if we stopped every power plant today, there will still be massive CO2 increases because of all the land use changes we've done and all the feedback loops in the Earth system. And so we've already, like, so to say, baked in a certain amount of warming in the Earth system. Like we've released this demon. We're going to see a warming planet for thousands of years, no matter what we do. It's just, how bad will it be? If we want to preserve life as we know it, like, we're not all going to die. Humans will go on, yada, yada. It won't be like some fiery doomscape yet, far in the future. But if we want to preserve life as we know it and the comforts we have and save as many lives as possible, we do need to do things like carbon capture.
Do you have any thoughts on what our best options are? There's a lot of, I've heard a lot of thoughts.
Yeah, the number one thing we can do is to not take the carbon out of the ground, put it in the atmosphere, and then expend energy to take it from the atmosphere and put it in the ground. We have to stop taking it out of the ground. The best way to store carbon is miles under the earth. And right now, by digging it up, we are unsequestering the carbon. So suffice it to say, leaving it in the ground is the best thing. The next thing we can do is, there's carbon capture on like coal-fired power plants are kind of silly because there's still emissions, and we just should stop using coal, and that would do a lot more. The big vacuum cleaner things, ideas like sucking the CO2 out of the sky, it's untenable right now because it requires a lot of energy, and we need these other non-carbon based energy resources. And we don't even have the energy infrastructure to power a fleet of electric cars. Like, if everyone turned to electric cars tomorrow, we wouldn't have the electricity infrastructure for it. We just haven't seriously addressed it yet, but we will, I hope.
Awesome. And then one last question. I guess, what role can or do microbes play in carbon CO2 sinks?
Microbes are everywhere, and they're doing some fabulous things. The hot topic right now is microbes in permafrost soil. So the Arctic warming twice as fast as the rest of the planet on average. The microbes are active during the winter. And so they are breaking down all of the frozen, juicy organic matter that's been preserved for thousands of years. It's essentially putting your like ground beef in the freezer and not letting it rot. It's like ground plant matter in the freezer of the permafrost soils of the tundras. And now we've unplugged the refrigerator or the freezer, and all those microbes are accessing that material. The thing that's troubling, though, is they're releasing primarily methane and not CO2. And that methane has about 30 times the warming impact that CO2 has, which is troublesome. National Geographic's had some really great coverage of that. I could put some links in about that. That's the biggest topic of microbes, but they play a role in almost everything.
My microbiologist coworker would be very happy to hear you say that. Awesome. Well, Bill, thank you so much for presenting. And so with that, Carrie Cresson here was also from James Madison University, and she's the director of outreach and STEM there. So Carrie, take it away. It's all you.
Okay, thank you. I just wanted to talk to you for a few minutes about some of the opportunities that come out of our center and then another center on campus. So I direct the Center for STEM Education and Outreach. And unlike most universities where STEM outreach is kind of done within one person does it in the College of Ed, or it's service for STEM faculty. The center is exclusively dedicated to K-12 STEM outreach. And we have a small variety of programs that got even smaller in the last year and a half, 2 years because of COVID. But I just kind of want to talk to you about the ones that are actually coming up this year that may be of interest to you or your students. When I say center, just so you have some context for this, a center in a university, a lot of people picture a big room with more than one office. And the center is me, just me. So we're only able to do so much, but we try to reach as many K-12 students in our region that can get to us or that we can get to them. And driving theme through everything we do is that it's no cost. I mean, if we could pay for subs so teachers could come, we would. We've helped subsidize buses for schools that couldn't afford buses. There's no cost to be here. We help subsidize lunch tickets on campus if that's a problem for families. So everything we do, we try to make as equally accessible as we can. Some pictures of kids we've worked with. So the center is just me running it. However, the reason that we're allowed to do the programs we do are because of a group of JMU students that volunteer for this. And they're not volunteering for service or because they have to do it for a class. And they hear about my organization called STEM Corps, and they come to me and they say, I want to spend my Friday afternoons at the Boys and Girls Club. So those are the types of students we're working with, and it's fantastic. And then in addition, for programs targeted at middle and high school that we're developing that are more research informed as far as the STEM research practices, we have faculty that volunteer to help us develop those programs. So I don't have an expertise in all the disciplines of STEM, and that's why we rely on faculty to make sure we're representing a good diversity of the disciplines and accurately. So the first thing coming up is we started this 4 years ago. It's called a Brain Bee, so think spelling bee, but neuroscience. The Brain Bee, so there's a national Brain Bee and then an international one. And so we host a regional one that's kind of Shenandoah Valley area. The winner to that goes to nationals, and the winner to that goes to internationals. Last year, the winner of our regional bee won second place at nationals, which made us very happy, and was the alternate for internationals. So what this looks like is it's for ages 13 to 19. That's determined by the national level. No cost at all. The students come here and we get them a t-shirt, we get them breakfast, we get them lunch on campus. And there's a competition, and all of the questions from the competition come from a free online book. And so all students are studying from the same resource. And they're ranging from, sometimes it's fact-based questions. Last year, because we did it virtual, we had some students that do neuroscience research present either like a human brain in the camera or their actual like histology research and ask a question in the context of their research. So it's kind of introducing these high school students to the types of neuro research that's done at JMU. And after that, they all go over to our neuroscience labs in the biology building, and we have the neuroscience professors and research students talk to the students and show them what they do and let them hold the real human brains and look at the microscopy images and all that kind of stuff. So we're going to try to have that again in person, and that will be in February. It usually runs from like 9 to 1, something like that. The other one that we're able to do, hopefully we'll be able to do this year, is we have it's become annual now. We call it the STEM Center Breakfast. We invite any K-12 science, math, STEM related teachers that can get to JMU by a Friday at 8:30 in the morning, and some JMU faculty that tend to be advocates for K-12 STEM education. So some of them are out of the College of Ed, some are in the science departments that are the ones that do a lot of professional development. And we have a big breakfast buffet, and then there's kind of some introductions and opportunity for the teachers that have needs to maybe touch base with some faculty that can provide some opportunities. And they get to talk to each other and not be around kids. And then we have a workshop, and we try to keep it timely. This year, we're going to have someone, we're not sure who yet, but someone that's working with BDOE on their new Math Pathways curriculum. But they're going to talk about practical ways to integrate data science of real important and interesting data into science and STEM curriculum. So what we insist on with all presenters is it needs to be practical within the constraints and that teachers have, and give them some resources they could walk away and try something next week if they wanted to. So we haven't opened registration for that yet. You can look for it. This is our website. You can email me if you're like, I'm going to remember this in December, so can you please shoot me an email? And then last, I wanted to just talk briefly about a program that we have been developing. This came out of my brain as a result of the increased awareness of social injustices over the past couple of years. And so it's a really long acronym, but I was proud of it. So this will be like a field trip model where a teacher can bring a group of students to campus, again, no cost. And instead of kind of doing what we used to do, which were some kind of traditional STEM quote activities, we are going to have we're designing experiences that are based on faculty research. So that might be a chemistry professor, it might be an engineering professor, and they're going to take the types of things they do in their lab with their students and modify and optimize it so it can be in 2 hours with middle to high school students on campus. And then as part of that, this isn't going to be an add-on, it's going to be what's kind of driving the whole project is students going to do some STEM thinking practices like data visualization, systems thinking, working with different types of models to understand the broader impact social equity piece that connects to that. So for example, the first one we've been developing, now an undergraduate did this summer with the professor in chemistry. Her research is on making biopolymers for different applications using chitin. And so our students, your students would come in and they do a very common chemistry practices, some quantitative reasoning to synthesize small plastic material from chitin testing some different variables. And then that will be, while that's drying and afterwards, they'll start looking at some different types of data visualizations and simulations on where our plastic goes that we are just like, yay, we recycle, good job. And all the way down to or over to the health impact of, say, children in Malaysia whose family are pickers, and some of the social and global issues with that. So that's the one we worked out. I've been thinking about this for like 1.5 years, and we just have the first one. It requires a lot of faculty time, which is hard to ask for right now. But we're hoping to offer 4 of these in the fall and offer maybe 2 of each, 8 over the course of a fall semester and spring semester until we can get some more funds to hire some more people to help us with this. And then I'm going to just leave these slides for you. This isn't my program, but I said I would share the slides. This is the Center for Advancement of Sustainable Energy, and Remy Pengel and her new hire, Dustin, run a bunch of K-12 education outreach programs that relate to wind and solar energy. And you can check out her website for the details. The one that she said to mention is there's an energy carnival, I think she called it, on October 2nd. And there's some opportunities for kids to make some solar panels or solar houses and then display them and get an award, things like that. So if you want more about that, I would email Remy or Dustin or check out their website. Yeah, and again, this is open to anyone that can get here and fills out the registration form, and when we ask for it, and there's no cost. And we won't make parking difficult. You can park right in front of where the building is. So.
Oh, it's awesome. Well, thank you so much for presenting, and I will certainly, I'll get all these up on my website and all of that. So thank you so much for joining us today.
Thank you.
Okay, and last but not least, we have Dan Tyler, who is a program manager with the Department of Energy Office of Science.
So thank you, Kim. Thanks for the invitation. I do work for the Office of Science in the Department of Energy, and I've been actually a DOE or federal employee for about 5 years. And before that, I spent 25 years as the education program manager at Thomas Jefferson National Accelerator Facility, which is in Newport News, Virginia, and hopefully called Jefferson Lab. So I'm hoping that most of you have heard of Jefferson Lab, and I'm actually going to talk about them at the end of my slides because they have a lot to offer in the state, and I just want to make sure that everyone's aware of that. So I started out my entire life, I wanted to be a teacher. And I was really good at math in school. And in high school, I started competing in math competitions. And then I went on to Virginia Tech and got a bachelor's and master's degree. So at that point, I hadn't gotten a teaching certificate or whatever it was called way back in the dark ages. So I was lucky enough to find a job at Jefferson Lab where they were looking for people, kind of STEM-minded people who were interested in education. So this job literally fell in my lap to work with classes of students that would come to the lab for field trips. And that was back in 1991-ish era. Some of you probably weren't even born then. So I worked there for a while and kind of worked my way up and became the program manager for their education programs. Along the way, I found the Department of Energy was doing a science competition called the National Science Bowl. And being a competition kind of person, I I used to do logic problems with my dad, and we raced to do logic. So it was pretty cool that there was a competition out there. And so I started being more and more involved with the National Science Bowl at Jefferson Lab. And then eventually I became the program manager for the National Science Bowl and another program for teachers at DOE. So that's kind of my story. You know, things just kind of happened. I just kept working as hard as I could, what I was doing, and things just kind of fell into place. That was pretty awesome. Been very lucky, and I look forward to sharing some of those things with you. But first, I would like to talk a little bit about the Office of Science. I'm not going to pretend to know what is going to be on the next screen, but I saw that one of the things to talk about was, you know, students are saying, how would we ever use this? What are we going to use this for? You just never know what's going to pop up. And I'm hoping that my screen advances. My mouse busted today, so I apologize if you see my fingers. So here are the Office of Science's major responsibilities. So they support a lot of fundamental research. A lot of what they do isn't going to solve a problem tomorrow, or maybe not even in 5 years, hopefully in the 20 to 30 year time scale. They're supporting 21st century tools for science. A lot of that is computer based. They have more than about, the number varies, 31 to 32,000 scientists across the nation who are working on problems. And the problems change every few years. And so they're doing their best to work on those. They have some large facilities that you'll see some that you hear about a little bit more that can cost excess of $1 billion. And it can cost or take up to 10 years to build them. So there's some pretty intense laboratories across the nation. And you guys have a great one in Virginia. It's Newport News. It's kind of midway between Williamsburg and Virginia Beach. So it's a nice little drive. You can go to Williamsburg for some culture, some history, go to Jefferson Lab, maybe when they open, maybe in the winter for some tours, and then go to the beach and see the ocean. So they also have 10 of the National Department of Energy laboratories are under the Office of Science, and Jefferson Lab is one of those. And they do a lot of research and development, coordination and integration with other federal agencies, with some security agencies. And I've highlighted some kind of targets or targeted focuses of late. Advanced materials, looking to see what can they do to a material to make it, you know, indestructible, or make it melt at, you know, when it's freezing, and just kind of things that you're not quite sure what you're going to need that for, but it's going to come in handy one day. Exascale computing is big. Cybersecurity, of course, is huge everywhere. Electrical energy storage, biofuels, solar energy, superconductivity, all kinds of things. DOE kind of has their fingers in it. When I say they support fundamental research, they not only support research at their laboratories, but they're the largest supporter of research in the physical sciences. A lot of people think of that the National Science Foundation would do that. It's actually DOE. So they do a lot of support at universities. And more so, this current administration is really big on supporting work at universities, and especially minority serving institutions and HBCUs. So let's look at the 17 DOE national labs. So I hope you can see on the screen different colored dots across the nation. The green dots are the Office of Science labs. And if you look on the eastern part of Virginia, it's a little too far east on the map than what it really is, but you'll see that's where Jefferson Lab is located. Also, you guys are in a great position so that you're close to not only Jefferson Lab, you're not too far away from the Princeton Plasma Physics Lab in New Jersey, and also the NETL, which is the National Energy Technology Lab, which is in northern West Virginia. So we've got a lot of rich resources nearby. And so you can see the labs kind of scattered around. Some labs are security laboratories, and those are in California and New Mexico. And then we have some other labs. For instance, the president, I believe today, is at the National Renewable Energy Laboratory in Golden, Colorado. So as you've probably heard, they're really serious about climate change and what they can do, and electric vehicles, some of the things that we just heard about that Bill was just talking about. The current administration is really looking at all the options to try to make some of these things. Within the Office of Science, we have another 6 offices, and they all focus on different parts of science. So I'm not going to go through all these, but it goes from computational research, and then there's basic energy science, looking at how you might manipulate matter, and biological and environmental research, they're doing a lot with climate and environmental systems. And then fusion, what kind of energy can we get from a star and what can we do with it? High energy physics, kind of like they're looking at space and time, and what's going on in space and time. And then there's nuclear physics, and that is looking at very, very deep inside the nucleus of an atom. And Jefferson Lab, which is near you in Virginia, I keep going back to that, they're a nuclear physics lab, and they're trying to study how the quarks and gluons interact inside the nucleus. So again, I'm not going to try to pretend like I understand a lot of what they do, but there's a lot there. And you are in my way. I know you can't see what I'm talking about. Okay, but anyway, so on the DOE website, you can, so this is the computer one. So they've got different stories and articles you could read. And again, their mission is to discover, develop, and deploy computational and networking capability to analyze, model, simulate, and predict complex phenomena important to DOE and the advancement of science. So each of those offices, they each have their own webpage. See an example there of the different web pages. And you could Google these or however you wanted to get there. So here I want to go back to, I'm so sorry. You never know how a mouse malfunction will affect your life. Okay, so this next page, you can see the graphic again of the United States and where the DOE labs are. And then our office, the Office of Workforce Development for Teachers and Scientists, internships for undergraduate students and faculty from small universities, and also graduate students to spend 10 to 16 weeks at a national lab. So for instance, if I pick a program, so Science Undergraduate Laboratory Internship, SULI. So a student who is enrolled in college as an undergraduate student, freshman through senior, excuse me, can apply to SULI, and they can apply to spend 10 weeks of their summer at any national lab across the country. So if you have an undergraduate student who isn't quite sure what to major in, they're a freshman, maybe they would just want to look at the different labs and say, you know what, I've never been to Idaho, let me see what they do, research that laboratory, and then they could apply to go there and do some research. Same thing all over the country. And on the other hand, some students might be interested in, say, fusion sciences, that maybe they go to a smaller school and that's just not really offered in one of their courses, or plasma science. And so they would want to apply to the Princeton Plasma Physics Lab, and they could go there, work with the scientists for 10 weeks, work on a project, and then kind of see where that takes them. The same thing works for students at community colleges. A lot of community college students stay closer to home, so but a lot of them can choose to go across the country. So I was just trying to think of an example. So speaking of the National energy renewable lab that I was mentioning earlier, several community college students from Virginia went there and ended up transferring to the Colorado School of Mines, which is in Golden, Colorado, I believe. And now they're working actually at that laboratory. So it's risky for a student to go off on their own and live on their own. That's not like the comfort of their college friends. I know they do that when they graduate from high school to go to college, but there's some kind of, there's a big group of people. So I'm really proud of the students that choose to do this. So this summer, even though they didn't have to leave home because we're still virtual, we had about 1,100 students who worked on virtual research projects, which I'm really proud of the scientists across the country who have been working with these students and making real projects for them. After the community college program, we have visiting faculty program. So this is where a professor who doesn't quite know where to start to do research, who's at a smaller college, might connect with the scientists at a lab, and then they can take 1 or 2 students with them to go to a lab for the summer. And then graduate students can do the same thing. So I mentioned this to you all, that if you have a student who is really interested in science, if you just kind of think about these opportunities for them once they're in college, it's hard for them to get these opportunities when they're in high school. But when they go to college, it's important for them to try to get some hands-on experience. And so for your math and science students, it's a good thing for them to do. So if you ever get that opportunity. This is kind of the same thing. And again, the same thing, but I want to talk about 2 other programs that you all might be more interested in for today, your current students. And that's the National Science Bowl and the Albert Einstein Distinguished Educator Fellowship. So the Albert Einstein Distinguished Educator Program or Fellowship is where teachers like yourselves would apply to come to Washington, D.C. for 11 months. So you would take the school year off and you would work for a federal agency, and you would learn about the roles of federal agencies in STEM education. And while you're there, they need the teachers' voices. Your voice carries a lot in Washington, D.C., and federal agencies like DOE, like myself, we're trying to, do things, make a difference for students. But we don't really, we think we know what we know, but we don't know what we don't know. And so, but you do know, because you're in the classroom every single day and you know these things. So the federal agencies need your voice so that they can allocate any funding that they have that's directed at STEM education and use it appropriately and in the best way. And this program gives you a seat at the table to voice your concerns, give your advice. And so you would be together with a small cohort of, 12 to 18 teachers or so on. You're invited to all kinds of opportunities around Washington, D.C. And it's a great experience for 11 months. And you can search Einstein Fellows on Google. The application for this program is actually open now, and it closes in mid-November. And we'll have some webinars and things hosted by, what you're looking at is a photo of last year's fellows. And a lot of last year's fellows will be hosting webinars on their experiences that they had while they were in DC. And of course, we'll have other former fellows as well. And again, these fellows were all virtual last year, but they all really made a difference, because we're all still working. And it's just incredible to see what the teachers have done over the past 25, 30 years that have been in this program. And in addition to federal agencies, 6 of these fellows work in congressional offices. And so they help write bills, they help They'll talk to constituents about problems and try to work with them together to solve some problems. So there are just a lot of really neat opportunities for you out there. I mentioned the National Science Bowl before, and I think you guys are all like in the Harrisonburg area. Do I understand that? I don't know. Tell me if I'm wrong. But anyway, so Jefferson Lab hosts one of the regional competitions for the National Science Bowl, and Harrisonburg High School went for years. So, and I don't know if they still do or not. So it's middle schools and high schools can compete in middle and high school competitions. And in Virginia, the high school competition is always the first Saturday in February, and the middle school competition is always the first Saturday in March. So if you have a team of 4 or 5 students, or if you have 4 or 5 students in your classes that you think might work together to form a team to do a question and answer type of thing, then I definitely encourage you to look into the National Science Bowl. It's a great bonding experience for you and the students, the winners of each regional competition. Hopefully this year we'll get to go to Washington, D.C. for the national finals. We just signed the contract last week for our venue, so I'm really hoping that we get to have it in person. The last 2 years, the national finals has been virtual, which has also been awesome. So even if we are virtual, even if the regionals are virtual, it's still a great experience. And I encourage you all to look into that as well. Okay, the next few slides are just some more information on those undergraduate opportunities. I just wanted to point out that the students receive travel and lodging and a $600 weekly stipend. And in the next 2 years, I think it's going up to $650. So we try to make it worthwhile to the students. It's certainly worthwhile to the laboratories, and the same thing with Sully. So the reason that we have the community college internships is to make sure that the community college students get a chance to be able to participate, because sometimes because they're still undergraduates. So community college students can apply to either CCI or the other program Sully. But if they apply to CCI, they might, their application is definitely gonna be looked at, because we wanna make sure that these are important students who are gonna make a difference, either if they just go into a technology field or if they switch schools and decide to get their undergraduate degree. So either way they go, there's a great need for them. So for the next 4 slides, I'm almost done here. Just wanted to talk a little bit about specific Jefferson Lab programs. So these are the undergraduate students at Jefferson Lab from 2019. And I wanted to wish me luck here, to play this little YouTube video of a student who talks about her intern.
I'm Lacey. I go to Virginia Tech, and I'm a rising senior in physics. And this is actually my 2nd year in Sully. And it's exciting because this year I'm doing more experimental physics as opposed to theoretical stuff on the computer. And I found that that's definitely what I'm a little bit better at than more theoretical stuff. I like doing more hands-on stuff. So I'm working with Pashupati, and he's a staff scientist in the test lab, and he spends most of his time in the vertical testing area.
Oh no.
And he tests the SRF cavities. And so I'm helping him with a side project where we take little bits of niobium, and we're trying to measure and also optimize the thermal conductivity of niobium. And so we have a small kind of nugget of niobium that's like a little rectangle. And then we wrap this really high resistance wire around the top. And when current goes through that wire, the top of the niobium is going to get warm. And then the bottom is hooked into like a cold finger that goes into a liquid helium bath at around 1.5 to 2 Kelvin. And then we measure the temperature gradient between those 2 areas. And then based on that and the size of the niobium and also like the current applied, we can actually calculate the thermal conductivity and then kind of optimize based on the purity of the niobium and different treatments, what's the best way to get the highest conductivity. This is my second year at Sully, and it's meant a lot for me to come back because I can do more experimental things this year. I've learned throughout the past couple of years that I'm a much better experimental physicist than a theoretical physicist. It's been my first experience in a professional workplace where they do research, and even though I'm doing a very small job, it feels like I'm really making a difference, and that some of the things I'm learning and understanding about niobium and how heat moves through it could actually really help people in the future. I've also gained a lot more confidence in my ability to do things in the lab. Pashupati, when he first explained what I was going to be doing, I was definitely very intimidated and worried that I wouldn't be able to do it or understand the science. And he did a great job of explaining things and always being there if I had questions, but also trying to get me to answer questions on my own and understand things. And that's definitely built up confidence for me. And I feel like going into the future as a research scientist, I'll have a good basis to start with.
But the students, you know, like she was saying, work on real projects. Here's another student working on so her mentor is a theoretical physicist. And so they worked on some simulations. And again, I don't know, I see pretty graphs and things like that, but it's kind of cool to see that, you know, here's a poster at a professional conference and the students are still working on, you know, they're doing an abstract, what methods they're going to use, the results, the conclusion, the graphs have labels, you know, all these things. So, you know, students will use it if they're going to follow this path, but even if they're not, they're still going to use things. Never mind, that's a whole different talk, so I'll just stop there. Okay. Other things that Jefferson Lab does, they do a lot of community programs. They have a great website if you haven't seen it. That voice that you heard coming up after that video was the intro to Frostbite Theater. They have a lot of small tidbit, you know, 2-minute experiments that are interesting, but you can't do them in your classroom. Like they might use liquid nitrogen, or there's a video series on butterflies. So things that they've done the work for you, and so you can just show the quick snippet to your students. And they also have puzzles and games. They host the practice standards of learning questions that probably some of you have used. Education.jlab.org is their website. It doesn't say it here in a moment. If any of you are 8th grade teachers, they have a program that's usually in person every other Wednesday afternoon. But since they're still virtual this year, they've opened it up to the state, and they do have some openings in their 8th grade program. So if you happen to be an 8th grade teacher, they actually will give you supplies. They would ship you the supplies that you would need to do some of these activities in your classroom. And the sessions are taught by 8th grade teachers. So as teachers, training teachers, and it's a great opportunity. And you can email me. I think my email address is somewhere, or put it in the chat box if you're interested, if you're an 8th grade teacher, or you can Google Jefferson Lab JSAT, JSAT, and you can find your way there. But they did want me to tell you that they do have openings in their 8th grade program. And again, their website is education.jlab.org. They have a lot of great just games, videos, lots of opportunities. You can also find your way to the JSAT program by clicking on teacher resources on the website. And finally, they, as well as, you know, Bill and everyone, you know, who's probably speaking to you, we're all looking to keep our students who are interested in STEM in STEM. And then we're also looking for ways to students who aren't interested in STEM, just to kind of give them some nuggets so that they know the basics, so that they aren't fooled by, what's the buzzword, misinformation, so that they know how to think about, you know, that doesn't quite make sense. So a lot of the programs that people across the world are doing is trying to help kids pick up some of those skills. And so it starts, you know, middle school programs and the high school internships, and then on to undergraduate students, graduate students, and so on. So That's the end of my presentation.
Yeah, thank you so much, Jan. It's one of those things where I keep learning about all the labs that the US government runs. And then I learn more and I'm like, oh, I didn't know that we also researched that and had an entire facility for it, which is very interesting. As also a huge fan of Jefferson Labs, I do want to make sure that all of our teachers do know that they have a bunch of lesson plans on Jefferson Labs, and I'll post it to LabVent so you guys don't if you don't want to look it up yourself. But if you are a Virginia teacher, they are aligned to Virginia SOLs. I just want to make sure everyone knows that, because that's huge for you guys, right? Because we got to make sure we're meeting our SOLs. And it was something that I just want to make sure I mentioned that, because it's something when I've looked at their website previously and I was like, oh my goodness, they're Virginia SOL aligned. How incredible. If someone were interested in connecting with a lab to hear more about what they do, find maybe a speaker for something that they're doing, what's the best way to go about that?
I'd say if you have an interest in laboratory, has what we call a laboratory education director. So there's a key education person at each national lab.
Awesome. That's really exciting. And I think especially, and certainly something I've learned with, the full switch to virtual, which sometimes I don't love, but it is really interesting to be able to connect people across the country virtually, so you can hear something a little bit different. I forward a lot of opportunities to my teachers. So it's certainly something I'm really passionate about, because I think that there's a lot of stuff out there for people, and especially in STEM education. And I want to make sure that, it's getting to the people who are really interested in doing those things. And I feel particularly fortunate to work with my tech teachers, because a lot of them have been teaching for, I think the last average I looked at was 10 years, which for science teachers is very impressive. And so I think, and these are certainly opportunities that the teachers I work with like to grab a hold of. Okay, and then I need to share my last slide with everyone. So I just want to thank all three of our presenters. I believe Carrie had to leave, but thank you, Carrie and Bill Lukens and Jan Tyler, for presenting today. I'm stunned at the stuff that I feel like I'm constantly stunned by, what we're able to accomplish and what people do. Thank our sponsors and we are sponsored by the Akamai Technologies, Amazon, Amgen Foundation, the Arnold and Cakes, the Gen Charitable Foundation, BAE, Clonmore Charitable Foundation, Gilead Sciences, Illumina Foundation, Jack Kent Cook Foundation, Jacobs Engineering, Janssen Pharmaceuticals, Lockheed Martin, May Family Foundation, Psychomedics Corporation, Spark Therapeutics, TC Energy, the Virginia Department of Higher Education, Vulcan Materials, and WestRock. And I just also realized that Commonwealth of Virginia as well. So good luck this school year. You'll be hearing from me in terms of just events that have happened and upcoming events that we are doing. And certainly please get in touch with me if you're ever looking for resources, you need a speaker, you just want to talk to someone because you have a question about classroom content. I know a lot of scientists who will be very, very excited to talk to you and tell you all about something. So I hope everyone has a wonderful evening. Thank you so much for joining us, and we'll be in touch.